Mr. True. All right. In this video, we're going to be taking a look at the slope and concavity of a graph of parametric equations, which we're not going to sketch, but there's, these parametric equations, the pair of them would create some kind of graph, and I want to find a function that is going to tell us the slope, the increasing or decreasing nature of the graph when t is equal to 0. Then we're going to move on to discussing the concavity of this graph when t is equal to 0. All right, so in calculus, what do we learn that gives us slope? Derivatives. First derivative. So when we think about first derivatives, our calculus notation that we use is dy over dx, which we may write initially, if we were working with a function in rectangular form, we'd be doing a derivative with respect to x of y, and that would, we could write as dy over dx. We could write as y prime, but that would not work well for this lesson. So when you're looking at a first derivative, it is effectively, a change in y over change in x, so dy over dx. Anybody have a problem with that? No? I do. This shows that we're taking a derivative with respect to x, that the independent variable is x. Well, in our pair of parametric equations, what's our independent variable? T. So you don't have any problem with that? Our equation of y and x are in terms of t, not in terms of x. They're both in terms of that parameter of t. So we need to sort of rewrite this derivative notation with an indication that we're taking a derivative with respect to t. That's what we really want to do. So we can break this up into a dy over dt over dx over dt. We can take a derivative of the y equation with respect to t, a derivative of the x equation with respect to t, and of course, when you divide fractions, what you're really doing is multiplying by the reciprocals. So we can take this dx over dt in terms of notation and show the division of that as a multiplication of the reciprocal. And indeed, when we, instead of showing a division of dx dt, and instead show it as a multiplication of dt over dx, the dt's are going to cancel out, and there's our dy over dx. There's our first derivative that we really want. So again, to find the slope, the change in y over change in x, to find the first derivative, the increasing and decreasing nature of the graph created by these two parametric equations, we want to just simply do the derivative of y with respect to t and the derivative of x with respect to t. And then take those two answers and just keep them in that change in y over change of x kind of pattern. So the derivative of 4t with respect to t is 4. And the derivative of x with respect to t, the derivative of t squared plus 5t plus 4 with respect to t, 2t plus 5. Okay, so now that we have dy over dx, which is equal to our 4 over 2t plus 5, if I want to evaluate that slope when t is equal to 0, well, then we just plug it in, and we get 4 over 2 times 0 plus 5, or in other words, we have a 4/5, which is greater than 0, right? That's a positive slope. So therefore, the graph is increasing when t is equal to 0. And that's how you find the slope of a parametric curve. Great. Well, way back in chapter 3, when we were learning how to use derivatives to analyze the behavior of graphs, what did we also talk about? It wasn't just increasing and decreasing nature of graphs. We also talked about concavity, and concavity means, well, we can talk about concavity using a first derivative. Quick tangent. This portion of just some graph, concave up or concave down? Concave up, which means the second derivative is what compared to 0? Greater than. But you should be able to also talk about concavity using the first derivative. What's the first derivative doing as you move left to right? What's the first derivative doing if your equation, if your function is concave up? Increasing. Not positive or negative, increasing. From this point negative to this instantaneous rate of change, well, it does look a little positive, doesn't it? Maybe at this point your slope is 0, your first derivative is 0. Now maybe it's maybe a positive 1, then a positive 2, and then a positive 3. But if your function is concave up, your first derivative is increasing. So your second derivative is either greater than 0 and your first derivative is increasing when your y is equal to some equation graph is concave up. Okay, so a little quick review of how you analyze concavity with the first and second derivative. Finding a first derivative, finding a slope of a graph created by a pair of parametric equations is pretty intuitive. Things get a little bit more complicated, though, when you go to find a second derivative. And before we continue, I'm going to write this 4 over 2t plus 5 as 4 times 2t plus 5 to the negative 1, just because it's going to aid us the rest of our work, so we don't have to use the quotient rule. But can anyone look at this first derivative and have any idea of how to tell me a second derivative, how to find the second derivative? At some point, we're going to use some kind of power rule. But do we just take this derivative again? Yeah, let's break this apart a little bit. How do we find the second derivative? We find the second derivative by taking the derivative with respect to x. This is what we would have done with rectangular sort of standard functions. You would have taken a derivative with respect to x of the first derivative, right? And then the 2 d's is why we have a d squared y. And you have 2 dx's, which is why we have the, okay, we don't wrap parentheses around the full dx. But it is, I remember when I first started relearning calculus, getting confused as to like, why is these exponents of 2 in different locations for the second derivative? And it's because of the way this notation works. So we have a first derivative. We have a dy over dx. It's 4 times 2t plus 5 to the negative 1. But this notation is showing that we're going to take a derivative with respect to x, and this independent variable is not x. That independent variable is t. So we need to, once again, kind of like break up this d over dx. We need to take, now I need to rewrite this derivative notation so that the end result, and I'm going to show a division of 2 derivative notations. And when we were to say, like I did over here, the derivative of y with respect to x is dy over dx, but since we don't have an independent variable of x, I wrote dy over dt equal to dx over dt. I need to do something like this over here, but have, when I simplify the derivative notation, I get not dy over dx, but d over dx. So we have the d squared y over dx squared, or that proper notation for a second derivative. And that is going to be what? What's the independent variable of dy dx in terms of? No, it's in terms of t. So we need to basically take a derivative. We need to show a derivative with respect to t. So we're going to have a d over dt. We're still going to find a second derivative by going through a derivative process. Our first derivative, we need to take a derivative of our first derivative to find the second derivative, right? The second derivative is the slope, is the derivative of the first derivative. And this independent variable is t. So we need a derivative with respect to t. But I need to show a division of some other notation so that when I sort of like, oh, I'm going to take this and divide by some pseudo fraction, but when I multiply by the reciprocal, I end up with d over dx. So I need to put a fraction down here, calculus derivative notation fraction, that when I multiply by the reciprocal, the dt cancels out. So I need a dt in the denominator. And when I show the division of this getting flipped up, when I justify that this is the correct answer, and I show that we have a pseudo fraction divided by a pseudo fraction, and we multiply by the reciprocal, the dt's cancel out, and we have a d over dx. So this numerator, like said, is dx dt, right? And just in case anyone's unclear, and for the YouTube video lessons, in case anyone's absent and needs to review this, instead of showing this division of a fraction, we multiply by the reciprocal, we'd have dt over dx, and then the dt's are going to cancel, and you have d over dx. Right? So this is that notation we've been using all year once we learned about second derivatives in chapter 3. We're just having to expand it a little bit for the recognition that we have a first derivative in terms of t, a first derivative that comes from the slope of a parametric graph coming from two equations working together. So we will find the second derivative by doing or walking through this notation of d over dt over dx dt. We're taking a derivative of our dy dx, okay? And that goes here. The dy dx are first derivatives in terms of t. We're going to take the derivative of that in terms of t, but then divide it by dx dt. So we have the derivative with respect to t of 4 times 2t plus 5 to the negative 1 over, let's go find our dx dt from our work. Dx dt from the original start of this problem was, and I didn't sort of pull it out separately, but it was in the denominator here, was 2t plus 5. So as we walk through this process and work and use power today, the negative 1 comes down, and we have negative 4 times 2t plus 5 to the negative 2 power. Now finishing the chain rule, the derivative of 2t plus 5 is 2. You all let me slip on that mistake a few minutes ago. Thanks a lot. Over 2t plus 5. Look, I was really just testing whether you were paying attention and you were just taking notes. So now we have 2 times negative 4 is negative 8. We're going to bring this base of 2t plus 5 to the negative 2 power down and hang out with the other 2t plus 5. And we have negative 8 over 2t plus 5 cubed is equal to our second derivative. The intention of the problem is to evaluate the increase and decreasing nature of our graph when t is equal to 0 and the concavity. So our second derivative, when t is equal to 0, is equal to negative 8 over 2 times 0 plus 5 cubed, which is negative 8 over 125, which is less than 0. Probably off the camera now. That'll be great. And so since our second derivative is less than 0, our graph is concave down. You're such good actors. So therefore, the graph is concave down when, and be careful, the concavity of this graph can change through different values of t, so be specific about where your conclusion is tied to when t is equal to 0. You leave off a time period on a free response question, you could very well not get that last point. And that is how you find slope and concavity of parametric equations.